going from -4 to +3, and this is graph of f. Okay? And it says that it consists of two quarter circles and one tangent line. So we're talking about this is a quarter circle, so this is circular, and this is circular. Okay, this would have been a big circle like this, and this would be a small circle like that. So it consists of a quarter circle and another quarter circle here. Right? This gives us a sense of how to find an area under the curve. Right? We usually would know that if we're given the radius, we can find an entire circle. So it's just a quarter of a circle, right? And the same thing for this. Right? We know the radius for this would have been a full circle. Radius would be 1. So this is just a quarter of that whole circle. Right? So that's the setup for us. Now here says that shown here above is f. Again, right? Remember I said these kind of problems are a bit tricky because they show you one graph and then they're asking something else. Right? So here they have g of x is equal to 2x plus, and I'm just going to go ahead and write it down right here. Part A, the setup is g of x is equal to 2x plus 0 to t, 0 to x, f of t dt. Okay? And here it says part A, I want to find g of -3. Okay? I want to find g of -3. Now g of -3 is just equal to 2 times -3 plus 0 to -3 f of t dt. Now you got to be careful with something like this. Now this part is easy. This part is -6. Now I was surprised that a couple of students didn't put -3 here. You put 3 in here. The work was very messy. So try to be careful with stuff. This is what it should concern you. You go from 0 to -3, but usually when you're taking the definite integral, you go from a small value to a bigger value, right? So you should flip it, right?
Yeah.
Right? And when you flip it, you introduce an extra negative sign. Right? So instead of plus, it's plus of a negative from -3 to 0, f of t dt. Right? Now, so this becomes -6 minus from -3 to 0. So we're talking about from -3 to 0. We're talking about this area under the curve. Right? This area under the curve. But this is a quarter circle with a radius of 3. Right? A quarter circle with a radius of 3. So it's a quarter of a circle, and the radius is 3, so it's pi times 3 squared, right? So far so good? You follow? So we get -6 minus 9 pi 4. And that's the answer. Many of you have plus 9 pi 4, right? That's because you forget to flip the boundary. Okay, next. G prime of x. You say, well, what's G prime of x then? Well, G prime of x is the derivative of g, and g is defined by this. So first term, the derivative of 2x must be 2 plus the derivative of the integral of f of t dt evaluating from 0 to x would have been f of putting the x in here times the derivative of the x, which is 1, right? So the answer is 2 plus f of x. That's it. Now, I'll give you an exception. Say, for example, if, this is the sign number, if g of x is equal to 2x plus 0 to 2x f of t dt, and you say, what's g prime? Well, g prime will be, well, the derivative of 2x is 2. The derivative of integral f of t dt will be f of 2x, right? Because you put 2x into the t, right? Times the derivative of 2x, which is 2. It would be this way, right? And that's the reason why I put a 1 right here to show you that you always have to remember that, because this problem may change. They may give you something more complicated like this. Okay, so this is the sign note. But anyway, so this is what we have for that part. Alright, lastly, g prime of negative 3. Well, g prime of negative 3 is just equal to 2 plus f of negative 3. 2 is 2, f of negative 3. F of negative 3 is 0. Right? So the answer is 2. Answer is 2. Questions? So puzzle 2. Let me erase this puzzle and go over the next part of the problem. Part B. Part B says, determine the x-coordinate of the point where g has an absolute maximum in the interval -4 to 3. -4 to 3, the same interval as the f. Maximum. We think of first derivative test. First derivative test of which function? G, because we're talking about g. Many of you get tricked. First derivative of g, so we're talking about g prime, and we want g prime to be 0. But g prime, remember what g prime was?
Yeah,
We just did it. Exactly. We said g prime was 2 plus f of x. And so if we set g prime equal to 0, we must set 2 plus f of x equal to 0. Right? If I set 2 plus f of x equal to 0, then I say, f of x must equal to -2 for me to find the critical values. Right? My point right now, the whole point of this process is to find critical points. Right? And then do the testing to see whether you will get a maximum or minimum on those points. We set it equal to 0 for g prime, but setting g prime equal to 0 meant that we set f of x equal to -2. So let's take a look at this graph. Where on the graph will we get y value equal to -2? Well, y value equal to -2 is right here. This is y value -2. The only place that will hit -2 is this point. And this is a straight line with a very specific slope, so we know that this must hit 2.5. So the critical value is at x equal to 2.5. So I put 2.5 right here. This is x value. G prime is equal to 0. Right? But G prime is also equal to f. No, not equal to f. G prime is also equal to 2 plus f. Right? 2 plus f. So let's pick a value that's less than 2.5. Let's pick, is going from -4 to 3. So we can put 0. How's that? We put 0 into f. Right? We put 0 into f. We get positive 3. 3 plus 2 is 5. Right? So it's positive value. So it means it goes up. We can pick a value that's bigger than 2.5. Let's pick 3. If we pick 3, that means it's 2 plus f of 3. Right? And f of 3 is a -3. So 2 plus -3 is -1. So it must be negative. So now we just justified it. That at x equal to 2.5, you will have maximum. So at x equal to 2.5, g has maximum. This is the justification. Yeah.
When it says absolute maximum or relative maximum, what is that?
Well, in this case, say for example, if you have another critical point where it can go back up again, this could be an absolute, it could be a relative max. You won't know unless you put that value back into the original function, back into g, if you have g. Right now we don't have it, and if this is the only critical point, and it seems to be the highest point, this is probably going to be the absolute. This will be the absolute max in this case. Okay, so here you got it. You have the answer for part B. Questions? Now we're going to go to part C. Part C says that find all the values on the graph G. Okay, we're still on G. We're not going too far away. We're still going on G. And we want a point of inflection. That means what? Second derivative. So part C, we want a second derivative test on G. So we say G prime. G double prime. But G double prime is equal to derivative of what is it? It's f prime, right? If G double prime is f prime.
Wait.
No, it's not. Sorry. Let's backtrack again. We say G of x is 2x plus 0 to x f of t dt. We say G prime is equal to 2 plus f of x. Right? So what's G double prime? F prime of x, right? F prime of x. And we are setting f prime of x equal to 0. Now f prime of x equal to 0, now we have a graph of f of x. F prime means it is the derivative of the slope becoming 0. Right? Do we have any? We don't have, do we have any place where the slope of the tangent line becomes 0?
No.
We don't. But that's not the only place to find critical point. Where else do we need to, what else can we find critical point? When, that's right, when double derivative, or this derivative is undefined. There's one place that is undefined. You have a cusp.
What about at -4?
Oh, here? Let's see. So it is possible. Maybe let's try that. Maybe we say possible x. We got x equal to maybe we can say it's -1. No, -3, right? We got 1, 2, -3, and 0.
Wait, so negative
Why
count?
can't it get -4? How does it go straight?
I hear. But this is the thing. When we're talking about point of inflection, we need two sides. There's nothing on this side because the graph ends right there. Right? So we won't count that.
Wait, so negative.
If this graph continues and the domain continues, then yeah, that point would have been a critical point to test. Okay? So now let's try that. So now we have -3 and 0. These are the x values, and this is the double derivative. The double derivative means this is f prime. This is undefined right here, undefined right here, and what we need to know is whether it's positive or negative. So between -3 and 0. -3 and 0, these are positive values or positive slope. What are we looking at? Slope. We're looking at slope. So these are the positive slope. On the other side of -3, -3 is right here. Are these positive slope or negative slope? Positive slope. In fact, okay, let me do it this way. Positive for slope means concave up for G, double graph. Right, concave up for G. Positive for this is concave up for G. Does that make sense? And then on this side, this is all negative slope. Negative slope for F means concave down for G. Right? We are trying to know about what G is by inferring from the F. You have to make a mental switch. Okay? So in this case, then we will say yes. At x equal to 0, point of inflection. Right? Because of the change of concavity. Does that make sense? Okay, good. Part D. So I'm going to just go ahead and write it down here. Part D. Part D says find the average rate of change. Average rate of change. Now, throughout this entire test, this is something that I've noticed that students just keep getting confused. There are times when you're asked to find average value, you don't remember the average value formula, but when there are times when you have the average rate of change, you remember the average value and misuse that in this case. The two different things. Average value and average rate of change are two different things. And here it says find the average rate of change for which equation? For F. Average rate of change on F on the interval between -4 to 3 is simply taking -4 to 3 and draw a straight line across and see what the slope is. You remember back in chapter 1 when we say average rate of change between, say, one value A to another value B in the domain, this is equal to f of B minus f of A over B minus A. Right? And then we have a discussion saying instantaneous rate of change will be taking B and A and very close to each other. So in this case, of change between -4 and 3 for f. For f, we're not even talking about g, we're just talking about f. It's simply f of 3 minus f of -4 over 3 minus -4. That's it. F of 3 is -3. F of -4 is -1. And 3 minus -4 is 7. So we get -2, 7. That's it. That's the answer. And you say, is it possible to have another value that will have the same slope? Right? This is the rate of change. Basically, it's named this. This is the secant line that cuts across the graph. The question is, can you find another place that will give you the tangent line with the same slope? Is it possible? I don't think so. Right? The slope for this entire segment is set. For this, it goes from here to here, from a undefined and then positive to a 0. Right? Over here, it's always positive, so all the slopes here are positive, all the slopes here are defined as one value, and this is a negative slope, so you don't have a point. Yeah.
Have you answered the second part of the question? Have you answered the second part of the question?
Explain why the statement does not contradict the mean value theorem. The mean value theorem says that in the interval, the function has to be differentiable. Is this function differentiable for the entire thing from -4 to 3? No, right? It's not differentiable at the cost. So therefore, it does not contradict the mean value theorem. Okay? The mean value theorem says that the function has to be differentiable throughout the entire domain. Okay? Any questions?
So, it's saying that it doesn't contradict the statement not to get any points.
What's up?
To say that it doesn't contradict the mean value theorem, to that not to get any points.
Well, you have to have the first one right before you get to the second one.
So it doesn't contradict.
It does not contradict.